Okay, specimen set 2, paper 2, let's have a look at rates. Okay, different kind of question. So this is an experiment where they have got some benzaldehyde. They have changed the concentration of benzaldehyde in the experiment across 5 different experiments. So the initial concentration of benzaldehyde in column number 1 was 0 in experiment 1. Then they've changed the concentration of benzaldehyde to 0.25 for experiment 2, then to 0.5 for experiment 3, 0.75 for experiment 4, and 1.00 for experiment 5. So we've done 5 different experiments with 5 different starting concentrations of this reactant, benzaldehyde. How have they changed the concentration? Well, they'll probably change the amount of benzaldehyde in each of the mixtures for each experiment and change the amount of water. Probably kept the total amount of solution the same, just by changing the amount of water, and benzaldehyde have changed its concentration. Okay, then what have they done? Well, they've probably measured the time taken for the reaction, and done at each time they've measured the concentration. So if you look at those 3 graphs, it's got the time taken for the reaction to complete in some way. Maybe it's like a disappearing cross, or it changes colour. The time taken for the reaction to finish for each of the initial concentrations. So for each of those initial concentrations, they've measured the time taken for the reaction to finish in some way. As I say, maybe it changes colour, maybe it obscures a cross on the bottom of the conical flask. Except time doesn't appear there. If time did appear there, if you do 1 divided by time, you'll end up with rate, or initial rate. So they've measured the times for each of those reactions to complete. We've done 1 divided by time, which is the rate. Rate is opposite to time. The longer the time takes, the bigger the time. The bigger the time, the slower the reaction. The quicker the time, the smaller the time, the faster the reaction. So you turn time into rate by doing 1 divided by time. And 1 divided by time is the initial rate. Okay, so they've just done that bit for you. And then what they want you to do is plot a graph. Well, let's have a look at some of the graphs that they could ask you to plot, first of all. They could ask you to plot each of the initial concentrations of the reactant, in this case it's benzaldehyde, against the time taken for the reaction to finish. That could be a question. And then you could draw a graph. If the graph is a straight line, then the gradient, which is the rate, is not changing. So the order with respect to that is 0, because changing the concentration has no effect on the gradient. The gradient is the rate. So if they ask you to draw a concentration up the y-axis and time along the bottom, if it's a straight line, the order with respect to the order of the reaction is 0, because the gradient is not changing, so the rate is not changing. If you end up with a curve like that of concentration against time for the reaction to finish, it's order 1. If it ends up a very, very steep curve, it's order 2. Because the gradients are changing, so concentration is changing the gradient, it's changing the rate. Okay. If they ask you to plot rate, 1 divided by time, and you get a graph, if it's a straight line, the rate is not changing. The rate is flat, so that is order 0. If it goes up in a straight line proportionally, it's order 1, so you double the concentration and the rate doubles. If it goes up in a steep curve like that, it's order 2. So quickly again, initial concentration on the y-axis, time to finish along the bottom, straight line, order 0, curve, order 1, very steep curve, order 2, because it's the gradients, you're measuring the gradient changes. If you're asked to do rate up the side, which is 1 over time, against the initial concentration of the reactant along the bottom, if it's a straight flat line, it's order 0. because the rate is not changing even though the concentration is changing. If it's a straight line going up, it's order 1, because doubling the concentration just doubles the rate, and if it's a curve like one on the bottom right, it's a order 2, because doubling the concentration actually doesn't just double the rate, it sometimes multiplies it by 4 or by 8, it goes up in the curve. So let's have a look what they're asking you to do. They're asking you to, from the concentrations and initial rates, draw a graph similar to the bottom set of graphs. Initial concentrations against rate, because they've got initial concentrations against rate, except they've done a little cheeky change. If they ask you to plot the first 2 columns, initial rate against concentrations, you're going to get one of the bottom 3 curves, flat line, order 0, straight line, order 1, curve, order 2. But they've put a cheeky little change in there. They've done the concentration squared. I'll explain how that changes things in a minute. Draw your graph. Plot a graph of initial rate up the side, so that's the bottom set of curves, but not against concentration, against concentration squared. And you'll end up with a graph like that. Now you might say initially, that is initial rate against concentration. It's a straight line. If it's a straight line, it's order 1, middle bottom graph, except it isn't initial concentration along the bottom. They've done initial concentration squared. Now that has a change. If they ask you to do initial concentration squared, what that does is it flattens a curve, bottom right, and makes it into a straight line. So initial concentration on the bottom right, against rate up the side gives a curve if the order of reaction is 2. But if they ask you to plot initial concentration of reactant squared, like they've done that mathematically turns a curve, bottom right, into a straight line. So it's order 2. Tricky question. Easier question now to compensate. It says that what is the role of cyanide? Well, it doesn't appear in the equation, but it does appear in the rate equation. It's having an effect on the rate, but it's actually not a reactant. It's not reacting, so it's a catalyst, because it appears in the rate equation, affects the rate, but it's not actually a reactant. Arrhenius equation. Right, this time they're asking you to plot a graph. So you just do what they ask you to do. They ask you to plot a graph, and it will look like that. They then ask you to work out a gradient. And when you've got the gradient, you can do something with that gradient. That gradient equals minus EA over R. So they ask you to plot a graph, like they have done there, of lnk up the y-axis and 1 over t along the x-axis. The gradient is minus EA, that's the activation energy divided by R. If you want to know why, if you actually look at the Arrhenius equation, there's a general formula for straight line graph with a straight line. Y equals mx plus c. Y equals mx plus c. Y is the lnk, and that is going up the y-axis. They've asked you to put that up the y-axis. Y is lnk, fine, equals mx plus c. ln A is a constant, so that is a constant c. In other words, they've that minus EA over RT is mx. M is the gradient line multiplied by whatever is on the x-axis. And what is on the x-axis is 1 over t. We've got 1 over t on the x-axis. In other words, m is minus EA over r multiplied by 1 over t. T on the bottom, that's the x-axis. So whatever is there before, in front of the 1 over t, because that's plotted along the x-axis, minus EA over r is your m, your gradient. If you want me to go over that this week before paper 2, a week on Monday, that's the 20th, I will do. When you get the gradient comes down, so that's minus. So your minus gradient in this case is minus 2.88 times 10 to the minus 4. When you plot it, that equals minus EA over R. Change the signs on both sides. EA over 8.31, which is R, equals 2.88 times 10 to the power of 4. Multiply the two numbers together, and you end up with the activation energy in joules per mole. That should be positive, by the way. The sign's wrong on that. It's a positive activation energy. Activation energy is positive. It's asked for it in kilojoules per mole, so you multiply by 1,000 to get so you divide by 1,000 to get joules into kilojoules, small into big, divide by 1,000, 2.39 times 10 to the power of 3, divided by 1,000 is 239. So that should be a positive. That should be a positive. And the reason they're both positives is I've missed my minus E off there. So minus and a minus is a plus. I'll go over that this week if you need me to.